All right, hi class. Today we're going to be going over some trig that is not necessary. Well, you could use it in our class, but it's not really necessary. But you are definitely going to be using it on the PSAT, the SAT, and Algebra 2 as well. So, I've talked to Miss May and Miss Gordon and Miss Garcia also. She teaches Algebra 2 if you're lucky enough to have her next year. And trigonometry was a big unit where they felt that it would be helpful to go over some things, some shortcuts. And I know from when I took the SAT and PSAT that these will definitely be all over that test, and it can make your life a lot easier, and help you compute some things without the use of a calculator. Great. All right. So the first thing I want to do is just explain this table. So this is a pretty standard trig table. The way this works, where I have this diagonal line, it means that all of these rows are all trig functions. So we've got sine, cosine, and tangent, all of theta. That could be in radians or degrees. It's just the measure of an angle. And on all these columns, those are representing the angle theta. So here we've got 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay. So the first one I'll do, we're going to try and convert these degree measures to radians, sort of go over that real quick. So 0 degrees is how many radians? That'll be 0 radians is equivalent to 0 degrees. You can always multiply degrees by pi over 180 to convert into radians. You don't have to do that here because 0 to 0 is just an easy one that I remember. And 0 times anything is 0, so you can do that one in your head pretty easily. 30 degrees and 60 degrees I think are very closely related, right? 30 plus 60 is 90. Those two angles are complementary. And you'll see as we go on in this lesson that these two angles, 30 and 60, are very closely related. So besides just being mathematically related, they also sort of have this nice little complementary characteristic where when we convert 30 degrees to radians, it's going to be pi over 6 radians. And then 60 is going to be pi over 3 radians. So that's how I try and memorize those two. 30 and 60 are complementary, so whatever's in the denominator is going to be sort of the opposite of what you see. 45, I'm also again using a method where I just look at the tens place, the first digit. So I see that 4, that's how I remember. It's pi over 4 radians. All right, and then finally by the time we get to 90, we are at pi over 2 radians. Because if you remember, 180 degrees is pi radians, so half of 180 is 90, half of pi is pi over 2. All right, so those are just quick and easy ways that I use to memorize these. I don't believe that they give you the conversion on the SAT. They may give you the formula to convert on the regions, but I think that if you can memorize these, it'll be a lot easier. And they're not that bad to memorize once you use them a lot. All right, so now besides just being nice fractions where I've got like an integer in my denominator, these radian measures and degree measures, these values of theta, also produce these very common trig ratios that we're about to look at. So sine of 0, sine of 30, sine of 45, yada, yada, yada. You will see those values come up time and time again in your mathematical future. And it's because they all come from very, very special right triangles. So bringing it back to geometry. So let's take a look here. So the first special triangle we're going to talk about is a 45, 45, 90. All right, so thinking about a 45, 45, 90 triangle, is that scalene, isosceles, or equilateral? Well, if two of my angles are congruent, we know that it is going to be isosceles. So besides just having two angles congruent, I also know that two of my sides are going to be congruent as well. So we see that opposite of 45, we have t. This side AC is labeled with a t. Since I know another side is also going to be labeled with a t, pick a side. Is that going to be AB or BC? So hopefully you said BC, because BC is also opposite a 45-degree angle. Additionally, we know that AB is opposite the right angle, making it the hypotenuse. The hypotenuse is never equal to one of the two legs. It's always going to be greater. So there's no way that this value could be t. So right now it's an unknown. I don't know what it is. Now we could use trig to find it out, like plug into your calculator, but we've got variables here. I don't want to use trig. I don't want to plug variables into my calculator. I want to try and do this on my own. So there's another method we have. If I know two sides of a right triangle, how do I find the third side? All right, the Pythagorean theorem. A squared plus b squared equals c squared, where c is the hypotenuse, a is one leg, and b is one leg. So t and t are our two legs here, so I'm going to plug those in. T squared plus t squared. C is really side AB, so just to make it look nice and relate to the diagram, I'm going to plug AB in. All right, so we have t squared plus t squared here. And I want to get AB alone. So the first thing I'm going to do is I see two like terms on this side. So if I have one t squared and I add it to another t squared, altogether, I have two t squareds. That's equal to AB squared. All right, and I want to find the value for just AB. So the way I'm going to do that is I'm going to take a radical on both sides. All right, I know on this side I'm going to be left with AB because that radical is going to cancel out that exponent. And since we're talking about lengths, right, real life values, I don't want negative numbers. This one's going to be a little trickier to simplify. So one thing I can do, because these are combined with multiplication, is I can separate them into two different radicals. Radical 2 and radical t squared. So what I'm looking for in these radicals is a perfect square, because then I can simplify them. Is 2 a perfect square? It is not. So that is going to remain radical 2. Is t squared a perfect square? Well, I hope so. It's got squared in its name. So the square root of t squared, just what times itself equals t squared, that would be t. So radical 2 times t will be equal to AB. So that means I can label here radical 2 times t. So anytime you come across a 45, 45, 90 triangle and you know one of the legs, you can save yourself a little bit of time here by just multiplying that leg by radical 2. For example, let's say that AC is equal to 4. I would immediately know that AB equals 4 times radical 2, because it's the hypotenuse, so, and it's a 45, 45, 90 triangle, so I just multiply the leg by radical 2. I know this isn't drawn to scale. I'm sorry if that's confusing, but we really care about the way it's marked up, not how long it is in centimeters or inches. All right, so that's a very special triangle that we see a lot and is going to be very helpful in filling out some of this trig table. So let's take a look at that trig table now. So I see that I've got this column for 45 degrees. All right, so I want to find the sine of theta when theta is 45. So let's, for the moment, let's just erase this and put a theta here. Or you know what, I'll leave it as 45, but I'll put in purple that we've got theta, just so everyone knows where my reference angle is. Theta, not a pretty theta, but whatever. All right, so if we remember from trigonometry, we have 3 types of sides in a right triangle. When looking at a reference angle, we can have an opposite side. So which of these 3 sides would be the opposite to theta? So opposite just means I go right from the angle, shoot out, and here would be my opposite side. All right, T. Okay, adjacent is going to be the other leg. So if this is the opposite leg, this has to be my adjacent leg. And really, maybe what I should have done first was label the easiest side. No matter what your reference angle is, this is always called the hypotenuse, right? AB. All right, so now what we're going to look at is what these, if I plug these values in, I have the sides into my trig ratios, what am I going to get? So what I mean by that is let's take sine 45, okay, and that's going to be, actually I should probably just write these at the top, right? Just so you guys remember. So, ka, toa. You don't have to memorize it that way. I think it's helpful to know SOHCAHTOA. Yeah, that's how some people memorize it. It's sort of ridiculous. It doesn't really mean anything. But opposite over hypotenuse is what relates to sine. So that fraction is going to be t in my numerator and radical 2 times t in my denominator. Okay. So one thing I can do right away is if I have a t in my numerator and denominator, I can cancel them out. And what you'll notice in all these examples, the variables will always cancel out. And we're going to be left with 1 over radical 2. All right. I don't really like having radicals in the denominator. It's not wrong, but I like to get them out of there. So the way we get radicals out of a denominator is by multiplying by a fraction that has that radical in the top and bottom. It's really just 1, right? Because radical 2 divided by radical 2 is 1. So we're not changing the value of this fraction because anything times 1 is just itself. So when I simplify this, 1 times radical 2 is radical 2. And then radical 2 times radical 2 is going to be equal to 2. So sine of 45 is always going to be equal to radical 2 over 2. That is always, always, always going to be the case. Now, we could do cosine, same method, but I'll show you when we plug in cosine of 45, you will see that it's going to be adjacent over hypotenuse, and adjacent is t, and hypotenuse is still radical 2 times t. So we're going to actually end up getting the same exact thing. So I could go through the steps again, but that would sort of be a waste of time. But that, if you remember something very important from trig, that should be no surprise to you. 45 is complementary to itself, right? 45 plus 45 is 90. And anytime you have a sine and cosine, and the two angles are complementary, that always means they're going to be equal. So sine of 45 and cosine of 45 are equal. Tangent, however, will be a little bit different. So tan 45 is going to be equal to opposite over adjacent, which will be t over t, or just 1. That one was pretty simple. Another thing that we can look at when we talk about tan is opposite over adjacent is sort of like combining the two of these fractions. And in actuality, if I take sine and I divide that by cosine, what I'm really doing is taking opposite over hypotenuse divided by adjacent over hypotenuse. All right, so keep the original fraction, change the sign to multiplication, flip this fraction to h over a, and we're just going to get tangent. So I can actually divide sine by cosine to get tangent. Radical 2 over 2 divided by radical 2 over 2 is 1. 5 divided by 5 is 5. 6 divided by 6 is 6. Anything divided by itself is itself. So this is sort of useful, very useful in the SAT, definitely in Algebra 2, knowing about this 45 degrees, that sine of 45 is always rad 2 over 2, cosine is rad 2 over 2, and tangent is always equal to 1. All right, so that's all for the special 45-degree triangle.